Hello, so today I will show how we can take the derivative of any function that could be discontinuous, could be continuous, could be whatever you want, and we can take the derivative of it. So we know that if we can take the derivative of a function, for example, f of x equal to 1, we can draw it like this. So it's just the constant function. So when we take the derivative, it's a constant, so it should be 0 everywhere. Um, and we know that if we can take the derivative of a function, then necessarily it should be continuous. But the inverse is not right. Not every continuous function has a derivative, like the following function. If you take a function that's 1, for example, and then x, this function is continuous, but it doesn't have a derivative at 0. So if you take the function f of x, that's equal to x if x is positive, and 1 if x is no, that's not x, that's x plus 1, right? And then if you take that, and then it's 1 if x is negative, then as I said, this function doesn't have a derivative at 0, and then we can show that. To show this, we have to calculate the derivative at 0. So by definition, so I will calculate the derivative from the right and then from the left and see if they are equal. If they are equal, then this function has a derivative. If they are different, then the function doesn't have a derivative. So we have f of x minus f of 0 over x minus 0. So from the right, f of x is equal to x plus 1. So this would be the limit as x goes to 0 plus to 0 plus of x plus 1. Then f of 0 is equal to 1, so that's minus 1. And then x minus 0 is x. So this would go with this, and this would leave us with 1. So the limit from the right is 1. Now the limit from the left, as you can expect, it should be 0, because the function from the left is constant, and the derivative of a constant function is 0. So that's the limit as x goes to 0 minus. F of x from the left is 1. F of 0 is 1, so that's 1 minus 1 over x, and that's 0. Okay? So the right limit is different from the left limit. So that means that the function f doesn't have a derivative at 0. Okay? But, and so that's a continuous function, but it doesn't have a derivative. Now, by what I said previously here, a a function that has a derivative, if a function has a derivative, that means that the function is continuous. But the inverse of this implication is not right. So surely by this theorem, a function that it's like this, so I'll have to change the colors. So if a function is like this is a function that equals, so this would be f of x equals to 1 if x is positive and 0 if x is negative. This function is surely not doesn't have a derivative because it's not continuous. Now, if you want to now for the fun part, how can we generalize the derivative and take the derivative of any function? So using the integration by parts, we will generalize the derivative. So let phi an infinitely differentiable function such that the support of the function phi, the support is defined by what? By all of the points x, such that phi of x is different than 0, and then we take all of the limit points. The limit points means that take the set x in R such that f of x is different than 0, and then take all of the sequences that converge in this set and include the limits to this set. So for example, q, we know that q is dense in R, so the limit points of q is R. So that's the one of the definitions of R. So that's just so this is the explanation of this. So you include all of the limit points. So now to generalize the derivative, so we know such that support of phi is compact in R. Compact means that there exists I an interval such that I is bounded and the support of phi is included in I. This is sufficient because support of phi is already closed, so we need just boundedness for compactness. So that's why I said so this is just the definition of boundedness. Boundedness means that there is an interval such that support of phi would be included in this interval. So now to find the derivative, we will just use the integration by parts. So we will define f prime of phi, the derivative of a function f is f prime such that for all phi we have this relationship. For all phi such that we have this condition here. So we should find f such that if we integrate f prime times phi, we find minus the integral f phi prime dx. So this is a lot, but let's apply it for this function. So take f of x equals to 1 if x is positive and 0 if x is negative. Okay, so now take this f of x times phi of x dx. Okay, so here it's a phi prime. So we have f is equal to 1 if x is positive, but it's equal to 0 if x is negative. So all of the negative values will be gone. So that would be the integral from 0 to infinity of f of x, f prime of x, dx. But f of x now, it's just 1. So that would be just the integral from 0 to infinity of phi prime of x. But as we know that the support of phi is compact. So here by the fundamental theorem of calculus, we have that this is equal to f of x evaluated at 0 and infinity. But as the support of phi, so let's imagine that phi has a support like this. So this is r, this is 0, and then let's say the support is this. Um, okay, the support is this. This is the support of phi. As x goes to infinity, it will be outside of the support. So by the definition of the support here, f phi of x would be 0. So that means that infinity phi of x would be 0. So this would be minus phi of infinity plus phi of 0. Okay, so that would be phi of 0. But this function here, phi of 0, we have what we call the Dirac function. I will use this notation, but this notation is not right because I didn't say anything about distributions. But I will use this for simplicity. So this would be the integral of r of the Dirac function at x phi of x dx. As I said, this is a wrong notation, but just for simplicity, with phi of 0 x, this was introduced by Dirac, the physician, or I don't know, it would be equal to infinity at x equal to 0, and then 0 if x is different than 0. This is the notation that's definition that is used by physics physicians. Right, so that's the function. So that means that f of prime of x is equal to the Dirac function of x. So that means that the derivative of this function is 0, but if x is different than 0, and it's infinity if x is equal to 0. And you can see that it's logical because we have a jump here. So here if we imagine that this function is continuous by like this, imagine that we take, so an explanation for this is, imagine that you take like an approximation of the function by a continuous function. So, or by a smooth function. So for example, like this, right? So the derivative of this function here would be 0. The derivative of this function here is 0, but here, because the function goes up really quickly, the derivative would be really big, really big. So as the function approaches the discontinuous function, the derivative would go to infinity. So that's the explanation. And that's how we generalize the derivative for any function that could be continuous, discontinuous. It should just only be measurable and integrable. Okay, thank you for watching, and leave a like and subscribe if you want.